PQ is an infinite current carrying conductor. AB and CD are smooth conducting rods on which a conductor EF moves with constant velocity V as shown. The force needed to maintain constant speed of EF is. Okay. So because of this PQ infinite current carrying conductor, there is a magnetic field into the page. But this particular magnetic field is not uniform all through EF. Right? This magnetic field, let's take any one particular point at a distance of x from this infinite current carrying conductor, and the thickness of that element, let's call it as dx. Let's see what is the EMF induced in this dx, and then we'll try to find what is the EMF induced between E and F. This is our first objective. Okay, so how do we do that? A tiny EMF is given by B into L into V. What is B at this particular point P? It is mu naught I by 2 pi x. Length of that element is dx, and the speed it is coming down is V. Integrating it, x is going from A to A plus. The length of the rod is how much? Yeah, this is B, right? A to B here. That would be mu naught I by mu naught IV by 2 pi into ln x from A to B. That is mu naught IV by 2 pi ln of B by A. This is the EMF induced in the rod, right? Because of this EMF, there is an induced current, and how that induced current will be in such a way that V cross B, when we calculate V cross B, B is into the page, V is downwards, so V cross B will be like this. So this becomes positive, this becomes negative. So the induced current direction is like this, right? So what is that? I induced is EMF by resistance, which is mu naught IV by 2 pi capital R ln of B by A. This is the induced current, but the same current is flowing through the rod again, right? And what happens when you place a current carrying conductor in the rod? It experiences a magnetic force. What will be the direction of that magnetic force? Fm bar is I times of L bar cross B bar. So L cross B, if you take, it will be upwards Fm bar. So I have to apply an external force such that it always moves with this constant velocity. In simple terms, the net force acting on the rod should be 0. So F external minus F magnetic is 0, or F external, if you take the magnitude wise, because we have already taken care of direction, is equal to F magnetic, which is BIL, right? Again, this force is also not a constant force, it's a variable force. Why? The magnetic field at different locations on the rod is different, right? So the total force is what we have to calculate over here. Let's do that over here. Again, taking a small element at a distance x, we'll calculate the force there and then we'll integrate it. So it is dFm is equal to V is mu naught I by 2 pi x, L is dx into the current is I is constant, I cannot be changed. Integrating it again, you will get it as mu naught I square by, this is I induced current, this I is the current flowing in the infinite current carrying conductor. So this is mu naught I into I induced by 2 pi ln of B by A. Let's erase this part. All right, so that would give me as mu naught I by 2 pi I induced we have found out here, which is mu naught IV by 2 pi r ln B by A into ln B by it is mu naught square I square V by 2 pi whole square into R into ln of B by A whole square. So here V by R is the one which doesn't have a square, so it can be brought out of integration. So it is V by R into mu naught into I by 2 pi into ln of B by A whole square. Mu naught I by 2 pi which can also be written as, I think option A seems to be the right option when looking at this, where this V is also sent into the square. Answer is option A.